Welcome to this video on solving the problem minimum health to beat game, also known as problem number 2214. In this challenge, we aim to calculate the minimum initial health required for a character to survive all battles. We'll explore the problem, break it down step by step, and develop an efficient solution. Let's dive in. In this problem, you are playing a game where your character must survive a series of battles. Each battle causes your character to lose a certain amount of health, which is represented by an array called damage. The value at each index in this array specifies how much health is lost in that specific battle. To help mitigate the damage, you also have a special item called armor. The armor can be used in exactly one battle, and it reduces the amount of health lost in that battle by the smaller value between the armor's strength and the battle's damage. However, the armor can only be used once, meaning it cannot be reused in any subsequent battles. Your task is to determine the minimum initial health your character needs to ensure that they can survive all the battles without their health dropping to 0 or below at any point. Essentially, you need to calculate the smallest starting health that is greater than the total damage taken across all battles after factoring in the armor reduction. The output for this problem is a single integer, which represents the minimum initial health your character needs to survive all the battles. Let's explore this with an example. Suppose the damage array is 2, 7, 4, and the armor value is 5. If you use the armor during the second battle, where the damage is 7, the armor will reduce the damage by the smaller value between 7 and 5, which is 5. As a result, the damage for that battle becomes 7 minus 5, which equals 2. Adding this to the other battles, the total damage taken is 2 from the first battle, 2 from the second battle after reduction, and 4 from the third battle, giving us a total of 8. To ensure your character survives, you need to start with at least 8 health plus 1 additional health to avoid running out. Therefore, the minimum initial health required is 8 plus 1, which equals 13. Now consider another example where the damage array is 5, 5, 5, and the armor value is 10. If you use the armor in any of the battles, it will reduce the damage for that battle by the smaller value between the damage, which is 5, and the armor value, which is 10. Since 5 is smaller, the damage for that battle is reduced to 0. The total damage taken is therefore 0 from the battle where you used the armor, plus 5 from each of the other two battles. This results in a total of 10 damage. To survive, your character needs at least 10 health plus 1 extra health, making the minimum initial health required equal to 10 plus 1, or 16. Let's look at one last example. If the damage array is 3, 3, 3, and the armor value is 0, the armor is ineffective because it cannot reduce any damage. In this case, the total damage taken is simply the sum of all the values in the damage array, which is 3 plus 3 plus 3, resulting in 9. To ensure survival, your character needs at least 9 health plus 1 extra health, making the minimum initial health required equal to 9 plus 1, or 10. This shows that when the armor value is 0, the solution is straightforward since the armor has no impact. Finally, let's discuss some important edge cases and constraints. If there is only one battle, the minimum health required is simply the damage from that battle minus the armor reduction, plus 1. When the armor is smaller than all the values in the damage array, it can only partially reduce the damage in one battle, so the total damage remains relatively high. On the other hand, if the armor is larger than the maximum damage in the array, it can completely negate the damage from one battle. For arrays where all the damage values are the same, using the armor on any one battle is equally effective. Lastly, for very large input sizes where the number of battles is up to 100,000, it's crucial to compute the total damage and apply the armor reduction in an efficient manner, ideally in a single pass through the array. To solve the problem minimum health to beat game, we need to determine the smallest initial health required for a character to survive all battles in the game. The damage array represents the health lost in each battle, and we have the added option to use a shield once to completely block the damage from one battle. Now, one way to approach this is through brute force. The idea here is straightforward. We simulate every possible scenario where the shield could be used. Specifically, for each battle, we calculate the total health required assuming the shield is used for that particular battle. This involves iterating through the damage array, skipping the damage of one battle at a time, and summing up the rest. We then compare the health required for all scenarios and take the smallest value. This ensures that the chosen health is just enough for the player to survive while using the shield optimally. The brute force approach, however, comes with significant drawbacks. First, its time complexity is n squared, because for each battle, we recalculate the total health required, leading to a lot of repeated computations. This inefficiency becomes especially problematic for larger arrays, such as when n reaches 10,000. On the other hand, it does have a low space complexity of 1, as no additional memory is used beyond the input. To address these inefficiencies, we can consider an optimized approach that leverages a key observation: the shield should always be used to block the battle with the maximum damage. This insight simplifies the problem significantly, as it allows us to minimize the required health in a single step. By focusing on the largest damage, we can reduce the overall damage taken in the most impactful way possible. This avoids the need for redundant calculations and makes the solution far more efficient. To implement the optimized approach, we start by computing the total damage from all battles, which is simply the sum of the damage array. Next, we identify the maximum single damage in the array, as this is where the shield will be most effective. Once we have these values, we subtract the maximum damage from the total damage to account for the shield being used. Finally, we add 1 to ensure that the initial health never drops to 0, as the player's health must always remain positive. This gives us the minimum health required using the formula, min_health equals total_damage, max_damage plus 1. The beauty of this approach lies in its efficiency. With a time complexity of just n, we can compute the total sum and maximum value in a single pass through the array. Additionally, it has a space complexity of 1, as no additional data structures are needed. This makes the solution not only fast but also memory efficient, even for very large inputs. An alternative method to solve this problem involves using prefix and suffix arrays. This approach precomputes cumulative sums to efficiently calculate the total damage while skipping a particular battle. Here's how it works. First, we compute the prefix sums, which store cumulative damage from the start of the array up to each index. Similarly, we compute suffix sums, which store cumulative damage from the end of the array backward. For each battle, the total damage can then be calculated by summing the prefix sum before the battle and the suffix sum after the battle, effectively skipping the current battle. From these values, we find the minimum health required. While this method also has a time complexity of n, as the prefix and suffix arrays are computed in linear time, it uses additional memory for the arrays, resulting in a space complexity of n. While effective, this increased memory usage is a drawback compared to the maximum damage approach, especially for large inputs. Given the different strategies we've explored, the optimized approach stands out as the best choice for solving the problem. The key to its effectiveness is the insight that using the shield on the maximum damage minimizes the required health. This method is intuitive, as it directly targets the largest reduction in damage. It is efficient, achieving n time complexity with 1 space, and it scales well to handle very large inputs without any performance issues. In contrast, the prefix/suffix approach, while also efficient in terms of time, uses more memory, and the brute force method is impractical due to its high computational cost. Each strategy has its trade-offs. The optimized approach relies on realizing the importance of the maximum damage, while the prefix/suffix method is more generalizable to variations of the problem. However, for this specific task, the optimized approach strikes the best balance between simplicity, efficiency, and scalability, making it the clear winner for our solution. In this problem, we need to determine the minimum initial health required for a character to survive a series of battles. Each battle reduces the character's health by a specific value, represented in the damage array. The twist is that the character has a one-time shield they can use to completely block the damage from any one battle. Our goal is to find the smallest initial health such that the character's health never drops to 0 or below at any point during the battles. To solve this, we need to focus on two main points. First, without the shield, the character's initial health needs to cover the total damage across all battles. Second, the shield can be used strategically to block the highest single damage value, which will minimize the initial health required. Finally, we need to ensure that at no point during the sequence of battles does the cumulative health fall below 0. These insights form the basis for our algorithm design. Now, let's break down the steps to solve this problem. First, we calculate the total damage, which is simply the sum of all elements in the damage array. Next, we identify the largest damage value in the array, as this is the one we would ideally block using the shield. From these two values, we can calculate the initial health required without the shield by subtracting the largest damage from the total damage. However, just having this value isn't enough, we also need to simulate the battles to track the character's cumulative health at every step. This ensures that the character doesn't lose all their health at any intermediate point. During this simulation, if we find that the cumulative health drops too low, we adjust the initial health upwards to keep the character alive. Additionally, we need to account for specific edge cases, such as when the array has only one element, in which case the shield should block it entirely, or when all damage values are very small, to ensure that the algorithm handles these scenarios correctly. The algorithm hinges on a few key insights. First, using the shield to block the largest damage value is the most efficient way to minimize the required starting health. Second, tracking the cumulative health during the battles is crucial, as it ensures that the character never dies mid-sequence, even with the shield in play. Finally, the algorithm dynamically adjusts the required health as needed to handle edge cases where intermediate health might drop too low. To implement this, the algorithm primarily relies on array traversal and a few key variables: total_damage for the sum of all damage, max_damage for the largest single battle damage, cumulative_health to track the running total of health during battles, and required_health to calculate the minimum starting health. The approach is efficient, with a time complexity of O(n), since we only make a single traversal of the array to compute these values. Space complexity is O(1), because no additional data structures are used, making this solution both time and space efficient. Let's go through an example to see how the algorithm works in practice. Suppose the input damage array is 4, 2, 7, 3. First, we compute the total damage, which is 4 plus 2 plus 7 plus 3 equals 16. Next, we find the largest damage value, which is 7. Using these, we calculate the initial required health without considering cumulative health: 16, 7 equals 9. Now, we simulate the battles. Starting with an initial health of 9, after the first battle, the remaining health is 9, 4 equals 5. After the second battle, it drops to 5, 2 equals 3. In the third battle, we use the shield to block the damage of 7, so the health remains at 3. Finally, in the fourth battle, the health decreases to 3, 3 equals 0. Since the health cannot drop to 0, we adjust the initial health upwards to ensure it never falls below 1. The final required health, in this case, is 10. Therefore, the minimum initial health required for the character to survive all battles is 10. This Python solution solves the problem of determining the minimum initial health required to survive a sequence of battles while utilizing a one-time shield to block the damage of one battle. Explanation of the code. 1. Input and problem understanding asterisk. The function minimum health takes two inputs: damage, a list of integers representing the health lost in each battle, and armor, an integer representing the maximum damage the shield can block in one battle. 2. Step 1. Calculate total damage asterisk. We first compute the total damage the character would take if no shield was used. This is done using sum damage. 3. Step 2. Identify the maximum damage asterisk. To maximize the shield's impact, it is logical to use it on the battle with the highest damage. We find this value using max damage. 4. Step 3. Determine shield's effectiveness asterisk. The shield can block at most armor damage. To calculate the shield's contribution, we take the smaller value between max_damage and armor using min max_damage armor. This ensures we do not overestimate the shield's effectiveness in cases where armor exceeds the highest damage. 5. Step 4. Calculate minimum health asterisk. Since the character needs to survive all battles with at least one health point left, the initial health required is total_damage shield_block plus 1. Here, total_damage accounts for all the damage, shield_block reduces the damage, and plus 1 ensures the character survives with at least one health point. 6. Return the result asterisk. The result is returned as the minimum health required. Complexity analysis. Time complexity asterisk. Calculating the sum of the damage list takes n, where n is the number of battles. Finding the maximum value in the list also takes n. Overall, the time complexity is n. Space complexity asterisk. The solution uses only a constant amount of extra space, making the space complexity 1. This implementation is optimized and handles edge cases such as small input sizes, large armor values, and scenarios where the damage list contains identical values. This is the Java implementation of LeetCode problem number 2214, minimum health to beat game. It mirrors the provided Python logic, using a loop to calculate the total damage and find the maximum damage value. Java-specific constructs like arrays and math.min are used, along with type declarations for variables. The function calculates the minimum health required based on the total damage, the shield's blocking capacity, and ensures at least one health point is left after all attacks. To solve the problem, we start with example 1, where the damage array is 2, 7, 4, and the armor value is 5. First, we calculate the total damage by summing up all the values in the damage array, 2 plus 7 plus 4, which equals 13. So, total damage is 13. Next, we identify the maximum damage value in the array, which is 7. This gives us max damage equals 7. Now, we calculate how much damage the shield can block. The shield can block up to the smaller value between max damage and armor. Here, min 7, 5 equals 5, so the shield block is 5. Finally, we determine the minimum health needed to survive. This is calculated as total damage shield block plus 1, which gives us 13, 5 plus 1 equals 9. Therefore, the minimum health required to beat the game in this example is 9. The output for example 1 is confirmed as 9. Now, let's look at example 2, where the damage array is 10, 20, 30, and the armor value is significantly larger at 50. First, we calculate the total damage. Adding up the values in the damage array gives us 10 plus 20 plus 30 equals 60, so total damage is 60. Next, we determine the maximum damage value, which in this case is 30. This means max damage equals 30. For the shield block, we take the minimum of max damage and armor. Here, min 30, 50 equals 30, so the shield block is 30. With these values, we calculate the minimum health as total damage shield block plus 1. Substituting the values, we find that minimum health equals 60, 30 plus 1 equals 31. This tells us that the minimum health required to beat the game in this scenario is 31. Now, let's examine example 3, which represents a situation where the armor provides no benefit. The damage array is 5, 8, 6, and the armor value is 0. Without any contribution from the armor, the calculations are straightforward. First, we calculate the total damage by summing the values in the damage array, 5 plus 8 plus 6, which equals 19. So, total damage is 19. Next, we find the maximum damage in the array, which is 8, giving us max damage equals 8. Since the armor value is 0, the shield block is effectively min 8, 0, which results in 0. Finally, we calculate the minimum health as total damage shield block plus 1. This gives us 19, 0 plus 1 equals 20. Therefore, the minimum health required to beat the game in this example is 20. To analyze the time complexity of this solution, we start with the operations performed. First, calculating the total damage requires iterating through the entire damage array, which contains n elements. Since each element is visited once, this operation has a time complexity of n. Next, finding the maximum damage value also involves iterating through the array to identify the largest number, which is another n operation. Determining the shield block, which is done using the min max damage armor operation, is a simple comparison between two values, making it a constant time operation, 1. Finally, the minimum health computation involves basic arithmetic operations like subtraction and addition, which are both completed in 1 time. Together, these steps lay the groundwork for understanding the overall time complexity of the algorithm. When we combine the time complexities of these operations, it becomes clear that the sum and max operations, both of which are O, n, dominate the overall performance. Since these operations are sequential and not nested, the total time complexity remains O, n. Moving on to the space complexity, the memory usage of the solution is minimal. The damage array is provided as input, so it doesn't contribute to the algorithm's space complexity. The only additional memory used comes from three auxiliary variables: total_damage, max_damage, and shield_block. Each of these is a scalar value, requiring constant space, or O1. No extra data structures are used, and the algorithm avoids recursive calls. As a result, the overall space complexity is O1, making the solution efficient in terms of both time and space. To better understand the efficiency of the current solution, let's compare it with a brute force approach. A naive method would involve simulating the game by iterating through the damage array and calculating the health required at each step, while repeatedly accounting for the effect of the armor. Although the time complexity of this brute force approach would still be O(n), it would involve additional computations within the loop, such as recalculating the shield effect multiple times, making it less efficient in practice. On the other hand, the optimized solution avoids this simulation entirely by directly computing the total damage, the maximum damage, and the shield block in O(n) time. It simplifies the implementation and reduces unnecessary operations. Both approaches have a space complexity of O(1), as neither requires additional data structures. However, the optimized solution achieves the same results more efficiently by minimizing the work done within the loop. To solidify our understanding of the time complexity, let's break it down mathematically. The sum operation iterates through the damage array once, contributing O(n). Similarly, the max operation also iterates through the array once, contributing another O(n). All other operations, such as comparisons, additions, and subtractions, are constant time operations, contributing O(1). Since these steps are performed sequentially, the total time complexity is the sum of these contributions, O(n) plus O(n) plus O(1), which simplifies to O(n). For space complexity, we see that no additional data structures are used, and only scalar variables are stored. This means the total space complexity is O(1). Both the time and space complexities demonstrate that this solution is highly efficient for the problem at hand. One of the most common mistakes when solving this problem is ignoring edge cases. For instance, if the damage array is empty or contains only a single element, it's easy to overlook how to handle these scenarios. An empty damage array might suggest no damage, but we still need a default health of at least 1 to ensure the character can handle any potential situations. Another common pitfall is misunderstanding the problem's goal. The objective is not to calculate the total health lost but instead to determine the minimum initial health required so that the character's health never falls below 1 at any point. Failing to understand this distinction can lead to incorrect solutions. Additionally, off-by-1 errors are frequent, especially when iterating through arrays or working with zero-based indexing. Being careful with array bounds and indices is crucial. Lastly, overcomplicating the solution is an avoidable mistake. Some may attempt to use advanced techniques like binary search or dynamic programming when a straightforward single-pass approach is sufficient. This not only increases time complexity but also makes the code harder to debug and maintain. Another mistake to watch out for is failing to handle negative numbers properly in the damage array. If the array includes negative values, which could represent healing effects, these need to be accounted for correctly in the cumulative sum. Ignoring them could lead to an incorrect calculation of the minimum health required. Now, looking at the interview context, this problem highlights a key pattern, ensuring that a running total, or cumulative sum, never dips below a certain threshold. This is a concept that appears frequently in problems involving constraints on sums or balances. The most efficient approach here is to use a single pass through the array, keeping track of the cumulative health at each step and noting the lowest point. From this, you can calculate the minimum initial health as 1, minimum cumulative health, to ensure the character's health always remains above 0. To impress interviewers, focus on communicating your approach clearly. Explain why it's correct and optimal, and explicitly mention edge cases you've considered. Finally, validating your solution with a few test cases, including edge cases, demonstrates thoroughness and confidence in your implementation. This problem also shares similarities with several related problems on LeetCode. For example, LeetCode 174, the dungeon game, requires determining the minimum initial health to survive a dungeon grid, making it conceptually very close to this one. Another related problem is LeetCode 135, Candy, which involves distributing resources while meeting certain minimum constraints. Additionally, LeetCode 581, Shortest Unsorted Continuous Subarray, involves identifying properties of a subarray, though the focus is different. Finally, LeetCode 53, Maximum Subarray, also deals with cumulative sums, but the goal there is to maximize the sum rather than constrain it. Exploring these related problems can help solidify your understanding of cumulative sums and minimum constraints, which are important recurring themes in algorithmic problem solving. While the single-pass approach is the most efficient solution for this problem, it's worth understanding alternative approaches and their trade-offs. A brute force approach would involve starting with an arbitrary health value and simulating each battle, incrementing the health until the character survives all battles. However, this method is highly inefficient, with a time complexity of n squared in the worst case, making it impractical for larger arrays. Another option is binary search. By searching for the minimum initial health that allows survival, binary search improves over brute force but still has a higher time complexity of n*log max_health compared to the optimal solution. Lastly, dynamic programming is a powerful tool for problems involving grids or more complex constraints, but for this specific problem, it introduces unnecessary complexity and is less efficient than the single-pass approach. Understanding these alternatives can be helpful for tackling variations of this problem or for demonstrating your knowledge during interviews, but the single-pass solution remains the most effective here. Great job following along. To wrap up, we reviewed how to compute the minimum initial health for a character to survive all battles. This problem showcased the importance of cumulative constraints and efficient iteration. Thank you for watching, and I hope you found this solution helpful. Don't forget to like, subscribe, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!